Okay, so I've been streaming a bit. Was a little busy. I was done with the previous chapter exercises, I think. Not even sure. Yeah, this one was very hard. No, actually I did this one, I think. It was the tree one, it was very hard. This one. Okay. So, two of the module topics I found particularly difficult to place were constraint kinds and polykinds. I think as we explore concepts like multi-parent time classes, it will become obvious why it's hard to say exactly where it belongs. Anyway, all that for later, let's go. Okay. In Haskell, we are hopefully all familiar with the idea of type parameters. For example, they may be typed as 1a, yeah, of course. We are at chapter 7, we know how this works. We also saw in the earlier chapters that we can use kind signatures to parameterize different kinds. Yes, of course. We even saw that we could parameterize over constraints. Yes. So let's take one step further. If we think about our original understanding of JDTs, we said they allowed us to embed constraints within our data constructors. In that case, where can we use a constraint parameter as a constraint? Uh, this, dear reader, is the magic of constraint kinds. Use a constraint parameter as a constraint. Oh, okay. So it takes this C, which is takes a type, returns a constraint. Oh, interesting. And then this JDT takes an X, returns an S constraint C, and applies this constraint C to the type X. And we need the extension to do this. Legal constraint, use constraint kinds. Cool. So what's going on here? We say that our type as constraint will be parameterized by some constraint C. We say that in order to construct as constraint C, we must satisfy C of X. The exciting thing is that our constraint is polymorphic. Let's look at another example, dict. So this one takes a constraint and just returns the dictionary. Okay, interesting. So dict is a constraint as a data type, true to the magic of JDT. Pattern matching on a dict will bring its content into scope. This allows us to write functions like this. Oh, cool. Is this what PureScript does? Because like when using PureScript code from JavaScript, there's an extra parameter. Okay, I think it's the dictionary for type classes, but I'm not sure. Maybe I'm saying something very stupid. So we're passing this constraint as a regular data type instead of a constraint, which is pretty cool and pretty confusing. Okay, perhaps interestingly, the following will fail to compile. This is because we haven't pattern matched. Although there is only one possible value, we still need to pattern match in order to bring the constraint evidence into scope. Oh yeah, let's call it AQ. Yeah, interesting and weird. Oh no. Okay. Well, the explanation was short. Let's take a look at the exercises. What's going on? We have only 2 exercises. Okay. So it's just a quick one today. There really isn't much to cover when we talk about constraint kinds, as it's hopefully quite an intuitive extension. Yeah. We are just extending a set of things that we can use as constraints to include type parameters. 1. Here's a super uninteresting list, which comes with an unfortunate restriction. Everything in the list must have the same exact type. Yeah, okay, it's a standard list. We can generalize this data structure to a constraint list, in which we say instead of every value as a type, we say every value's type satisfies this constraint. Do it. Think about the nil and const cases separately. Which constraints can the nil case satisfy? Okay, I'm gonna open the explanation back here. So we can have a C const which I'm assuming we can write like this probably. And then we have a CNIL which has no constraint. Oh, sorry, this one is an X. Yes. Okay, it was pretty easy. By using what we know about rank and types, I forgot everything about rank and types. Write a function to fold a constraint list. Note that we'll need the folding function that works for all types to implement some constraint C. Wink, wink, nudge, nudge. Okay. So we are folding a list. Which is gonna have a folding function. It's gonna take our constraint list of C, and I don't know what's this is going to return right now. So Haskell exercises 07 Kaba REPL. we're gonna implement one of the folds. I'm a little confused because our foldable function only have the constraint. I think I can use or we can use fold map maybe as inspiration. So we're gonna return an M, which is a monoid. And now we have some function here, which is gonna take something, which I guess a constraint list of C, and it's gonna return our M. And since it told us that we need rank and types, I already know that we're gonna have to do this. This one is gonna be empty. Oh, hi. It's a small word. And this one, full sequence of x. And sorry, we have a function f, x, xs. Yeah. And this one is gonna be f of x. And then we append it to full constrained list f xs. Seems like it doesn't like my signature. Why is it? Because this function takes just one element. And we don't care about the function here. Yeah, who cares? It's fine. Okay. Can move to C. Often I want to constrain a list by multiple things. The problem is that I can't directly write multiple constraints into my type because the kind of EQOR isn't a type constraint. It's actually a kind error. There is hope, however. A neat trick we can place to define a new class, whose superclasses are all the constraints we require. We can then write an instance for any A who satisfies those constraints. Neat, right? Yeah. Write this class instance so that we can have a constraint that combines a monoid A and a show A. What other extension do you need to enable? Why? Okay, I'm not entirely sure how. So this is gonna be show A, monoid A, constraints A. interesting. Is it just, I don't know what, I don't know what I'm doing, honestly. The constraint show A is no smaller than the instance head constraints A. Use undecidable instances to permit this. Okay, if you say so. Okay, what can we do now with this constraint list that we couldn't before? There are two opportunities that should stand out. I guess we can either show it or combine it. I don't know. Two, recolor list. Data H list, which takes, yeah, it's an heterogeneous list, okay. Ideally, we'd like to be able to fold over this list in some way. Ideally, by transforming every element into a given monoid according to interface of some constraint. To do that, though, we need to know that everything in the list implemented a given constraint. If only we had a type family for this. Write this fold function. I won't give any hints to the definition, but we will probably need to call it like this. It's gonna be painful. So we need the type family. I'm gonna reopen the type family chapter. Come on. Oh, it's already open, okay. So yeah, type family is a function that works on types. Yeah. So we need to write a type family because he gave us this int, which can apply a constraint to every element of the list. Okay. So this is gonna take something here, something. It's gonna return a constraint, right? Because that's what we need. Oh, this is hard because I probably waited too much time between the exercises, which is probably better to learn because I'm forced to rethink about things. It's very hard now. Uh, so we're gonna have, yeah, we're calling it on a list. So we're definitely have an H list here as a parameter. Which is probably we can use this one. So we can have, I'm gonna have a list of types here. And if you have an empty list, we're gonna return the empty constraint. And then we can have our list. And we have to return something here. Does this work? No. Wildcard not allowed. Okay, thank you, GC. Very useful. So we need to apply a constraint to this type. So we are gonna have to pass another thing here, which is gonna be something that goes from I guess it's gonna be like this. Something goes from a type to a constraint. Which we don't need here. Or we're gonna need here. It's gonna be so this thing now is a constraint. How does this work? Is it gonna be like this? Come on. I'm getting errors. Oh, I'm only building a constraint, so I don't need this one. And I have an error. Legal qualified type. Indications for a closed type family and type family declaration. Okay, what does this mean? I have an idea. Yes, I think I'm using the wrong syntax. Because this is not a function signature, but I'm building a constraint. So this one compiles. The problem is that I need the constraints for all the rest. Oh, here. Unlike tuples, constraints are auto-flattened. Okay. So I think I can just do this. I can just build a nested tuple, which will be flattened by the compiler. Yes, this one works. Or at least I have no errors for now, which is already something. Yeah. I'm at chapter 7, almost done. It's getting trickier and trickier. So now to write this test function, we need two pieces. We need a fold function and we need a TC proxy. So this TC proxy I guess it takes a constraint as a parameter. sorry, it takes a constraint builder. So it goes from type to constraint and returns TC proxy. I don't know if I've been able to write this without this help here, because this is getting tricky. Okay, then we need this fold function. So this fold takes a TC proxy. See? It takes a function which is related to the proxy. Can we write it like this for all x, cx? Takes an x. Oh, we're folding, so we're going to return a monoid. And we're going to add a monoid constraint here. Okay. And then we are getting an H list of XS. So if you're folding H nil, we're going to return empty. Oh, and we're returning M, of course. Okay, no errors for now. I think we're missing the trickiest part. So I'm not sure we need to do anything with this proxy. Just needs to be there. Then we have function. Then I'm gonna have an hconst of x and some rest of stuff, just to try that everything is going fine. Let's try this. It works fine. So we're gonna apply this f to x, and then we're gonna append it to fold. Oh, we need fold cf xs, and we get an error. Could not deduce c of x arising from the use of f. Okay, I guess we need our h constraint too then. So we're applying a constraint to our list. Which is going to be an excess. And ABC. Okay, well, looks like it's working. So I wonder why we need this proxy. I'm gonna write another version which doesn't use the proxy. I want to see what happens. Could not deduce h constraint c0 excess from the context h constraint c excess. No, I'm gonna assume it's a way to tell the compiler this C here is the same C as here. I'm not sure why it's needed though. Yeah, this is definitely something that if I try to do on my own, I would spend like hours changing random things, and then spend another hour on forums and Stack Overflow trying to figure out what's going on. Probably will never get to the solution. Okay, I can try writing this test function now. I guess we're just fixing show. Looks like it's working. I guess we can try it. So we can test and h counts of 1, h counts of true, h counts a h nil. H counts is applied to too few arguments. Is it? Okay. Yeah, it works. I want just to take another look at this error here so that if I see it another time, maybe I remember that using a proxy is a way to solve it. Yeah, so this is a way to pass this type here, which is it's a function that builds a constraint, actually, a type level function, to pass it here without having to actually building a value, because it's obviously impossible to build a value of this type. And so we pass it as a proxy. Yeah, no. Let's try with C, no, B. Oh, why do we need the proxy to point out which constraint we're working with? Why does GHC not like it if we remove it? I'm not sure. And I guess GHC needs a little handholding sometimes. We typically define full map like this. Okay. What constraint do we need in order to use our A to M function on an H list? You may need to look into the equality constraint introduced by the JDT and type families extensions written as tilde. Yeah, I used this one once, and I was doing some weird stuff with type level comparing stuff to a function that could only be applied to a data type which was greater than another data type, which I thought was a very clever thing to do for authentication, but it's probably just stupid. Okay, we have to write fold map for each list. H fold map. So we're building a monoid. Now we're having Well, let's just copy that signature for now. We have an H list and we're returning an M. So obviously here we have a problem because there is no way to know that this A is the same as the elements here, also because the elements here change type for each element of the list. So we need to do something like this. Just gonna keep it very simple for now and add the rest of the pieces. So do we need the same stuff before? I don't know. I think I'm writing the same function. I am writing the same function. I'm confused. What's the difference here? What constraint do we need in order to use our A to M function on H list? Oh, so I can write this. I guess the point of the exercise is to be able to do this. Okay, let's write the const case and see what happens. H fold map fxs. So this is gonna complain, of course, because it can deduce that x is equal to a. So we can do a h constraint. No. What's the kind of this thing? Takes a kind, takes another kind, returns a constraint. So we have our h constraint, which we're applying to XS. And we need to do something here. Wildcard not allowed in a constraint except as the last top level constraint of a type signature. Yeah. So we can try doing this. All right, we have to pass a constraint builder here, so we can do this. looks good. Looks good. Let's try it. Can hfold map. So this is the same thing as this one. It's just that we don't need the proxy, which feels much easier to me. I mean, there's a different usage, probably. Oh, because here we are basically making our heterogeneous list into a non-heterogeneous list, I think. Because only if I do hconst 1, hconst true, hnil, I guess I'm gonna get an error. Yes. Oh, sorry. I get an error because I'm missing a piece. No instance for numbool. Yeah. So I take what I said back. So this is much less useful than this fold here. Okay, it was quick, but not painless. I take a peek at polykinds. Okay, the explanation is not too long. Let's see how many exercises are here, because I want to go to sleep too late. A lot of exercises. Let's start and see where we get to. Return with a module whose focus is on kind polymorphism, which is enabled by the polykinds extension. We'll find out where to use it and wonder how we could do without it. I don't know. I doubt about this. Haskell in general loves the notion of type polymorphism. Let's take a nice familiar function, id, which takes an a, returns an a. This function is totally polymorphic in its a variable. You can give it any type of value and you get a value of the same type back. Now let's write a type family to do the same. So a type family ID, which takes an x of kind A and returns a kind A. Yeah. Okay, this is the error. JHC begins to marvel of modern engineering that it is, tells us exactly what to do here. We have a kind variable, which means that we're trying to make our type family polymorphic in its input and output types. In order to do that, we're going to need kind polymorphism and hence polykinds. Let's look at another example, a rumble proxy type. If you type this into GHCI and then ask for the kind, you'll get nothing too surprising. A equal proxy. I can inject K. Yeah. We see that GHC infers that the kind of this type to be a type constructor of one type argument. Just like maybe or IU. However, let's turn on polykinds. Yeah, GHC has now looked into the constructors of the type and noticed that we don't use type parameter as a type. Unlike maybe, for example, whose parameter is used in the just constructor. As a result, it has said that we can use any kind for argument. It's now kind polymorphic. There's really not much more to this extension. I'm lost. Where is it? Where was I? Okay. Just as we don't have to write this, so id string, id int, id bool, we don't have to do this at the type level. The only thing worth mentioning, which won't bother us too much in these exercises, is that kind polymorphism as a trick that type polymorphism doesn't have. You can pattern match on types within kinds in a kind polymorphic type family. Oh. uh, don't panic. We'll take a look. Okay, so we have a data secrets, and we have a type family smuggler, which takes a type of kind k, returns a kind k, something of kind k, where smuggler of IO secrets a. What? It seems that while we say that this function would work for any kind, we actually can inspect the kind in our rules. As a result, type families aren't necessarily parametric. Okay. Couldn't match expected type A1 with actual type IO secrets A. I guess that's because we're returning an IO of A. Here, I don't know. This is very confusing. The error is that we couldn't match IO secrets A with A because we say this function will work for all A, we therefore can know anything about the value. With type families, however, we can look at the kinds involved as more arguments to the function. The smuggler family has two inputs, the type X and the kind K. The extra power with kind polymorphism makes for some exciting opportunities to abuse the type system, as we'll see in exercises. Okay, I'll go on with the exercises and maybe I'll understand this stuff a little better. Okay, 1. Let's look at the following type family to build a constraint. We have a type family all, takes a constraint constructor, a list of types, and returns a constraint. Okay, yeah, I already did this in the type families exercises. Why does it have to be restricted to type? Can you make this more general? We can try for sure. Um, Will this work? Who knows? No one knows. Doesn't work. Oh. Is it just a typo? Yes, it is. Okay. B. Why does it have to be restricted to constraint? Can you make this more general? Why is this harder? I'm gonna copy and paste it so we keep our correct solution up there. I'm gonna make it all double quote. So I'm gonna assume that this won't work. It's way too easy. What? Why is this harder? It's not harder. I think I did something wrong. I'm confused. This was extremely easy. It wasn't harder. Did I mess something up? No, I don't know. I'm gonna assume that this will break if I try to use it. I'm going to try. Was it expecting one more argument? Oh, of course, the list too. So this one works so far. Let's try with the other old implementation. That both work so far. Okay. Oh. Okay, this one works. It's obviously not the correct implementation, but it should be enough to check if it's correct at type level. And this one works too. Mm. Let's try applying them. So let's try showing h const 1, h const true, h nil. Oh, I'm wrong. Okay, I'm getting an error now. I'm getting a lot of errors. Couldn't match type P with string. P is untouchable. Uh, oh, my bad. Could not deduce all quote show x1 arising from a use of show quote. Why not? I guess it's not possible. Or at least it's not possible with my knowledge, which is very limited. Sometimes we're working with a lot of values and we like some way of identifying them for the compiler. We could make new types, sure, but maybe there are loads. Oh, there are loads, and we just don't want the boilerplate. Luckily for us, we can introduce the new type. So it's this data tag, which takes a name, which is a symbol, takes a type, and holds the type. Oh, cool. Symbols are all well and good, but wouldn't it be nicer if we could generalize this? So can we tag this with a constraint? Oh no, we can't. Oh yes, we can. We actually can. Okay, cool. That's pretty weird. That's cool. Can we generalize type? If so, how? If not, why not? Expect the type, but A is kind T. Right. So I think we can't. I think at runtime we only have type. We can have other kinds. Often when we use the tag type, we prefer some type promoter with data kinds over strings. Why do you think this might be? Because it's easier to combine them? I mean, aren't these essentially variants? So that we have a list of values instead of infinite number of strings. I'm assuming, I don't know. I'm gonna do this one and then I'm going to sleep because it's getting late. We can use the following to test type level equivalence. Data A, this looks like a sad face, a crying smile. A crying B, where what? What? How? What's going on here? Yeah, I am crying. I'm extremely confused by these two lines here. So I guess it's basically saying that B has to be equal to A because B is A. Yeah. What do you think the kind of crying smiley is? So it takes a kind, takes another kind, returns another kind. Oh, there's an error. Okay, yeah, this one is not possible. Does polykinds make a difference to this kind? Um, I don't know. I mean, we're getting a star here, where I guess we get a type without polykinds. Yeah, it's already set. Regardless of your answer to part B, is this the most general kind we could possibly give the constructor? If not, hint, it's not. It's perfect because I was going to answer that it was impossible. What more general kind could we give it? How would it tell this to GHC? How can it be more general than this? I have no idea. So I basically cheated for this one because I asked GHC. This one, no, it's not a typo. It's type level black magic stuff. I don't know. It actually works. So if we put B in here, this thing doesn't do anything. If we put A here, we're basically saying that A and B have the same kind or the same type. Actually, the same type. Yeah, it's very weird. So here, I guess we get the star instead of star is type actually though. I think we have to define this again. Um, I don't know. I don't see any difference. Oh yeah, okay, yeah. With polykinds, we get the this case here because these ones are actually polymorphic. Well, without it, we will only get types, so we get 3 stars here, I think. I think the kind will be okay. Regardless of your answer to part B, is this the most general kind we could possibly give this constructor? If not, hence it's not. What more general kind could we give it? And now will we tell this to GHC? I don't know. I guess I'm gonna check the answer for this one. And then I'm gonna go to sleep. Defeated. And crying like the smiley operator. GitHub. Tom. Haskell exercises. Doing polykinds. Yeah, okay. I got it backwards, but I got it right. We could give it a kind of KL type, knowing that K equals L. Whenever we see a REFL, we'd have to annotate it explicitly to get here, though. I guess so. I don't know what the point of doing this would be, and I don't know. I give up. That's enough for today. These are so hard. I have to think way too much. Yeah, thank you for watching. It was a bit of a fail stream. Very few exercises and struggled a lot. But I guess that's what I can expect from the next chapters too, because things are piling up and get harder and harder. But I really like this repo. I mean, it's very very clear and it's very nice doing these exercises. Yeah, I know. It's not so good when you're the one struggling, though. I'm kidding. It's good. It's the best way to learn things. Well, I'm almost done. So depends on how long these chapters are. Probably be done in next weeks or so. Thank you for watching and have a nice day or night, whatever time zone you're in.